So Michael Faraday was binding books, and one of the books they were going to bind to sell was a book on all these papers on electricity and magnetism, so people could then, this would be like a big seller among physics people. And Michael Faraday said, you know what? Rather than just put any article in there, I'm going to repeat the experiments to make sure that only the best articles go in there, the ones where they're really reporting good results. Well, as we all know of Faraday, probably the best experimentalist of the 19th century. No education, but really good with his hands, really good with systems. In fact, so good that Sir Humphrey Davy hires him as a chemistry assistant because he's good at that also. In urban America, 30% of our population, there are kids who never get to do any experiments. They never get any equipment. In fact, in affluent districts, it's the low-level kids who never get to do any experiments. Oh, the high-achieving kids, oh yeah, you can do experiments. Oh, we have that lab. You can have a special lab period. And I am convinced that all over America, not Michael Faraday's, but perhaps the next Michael Faraday, and we're not even finding that kid because we're never even allowing us to find out if they have other skills that, oh, no, you can't do a vector cross product? Please don't go near physics. But I'm really good with my hands. Like, well, no, it's the vector cross products. That's the filter. It's scary. But you know as well as I do that you leave you go to the game in the afternoon and you watch this and you say, I had no idea you could play field hockey like that. You go to the concert and you see somebody playing the saxophone, you say, I had no idea. Because all you see is they're struggling in physics. And then you see, my God, do they have talents that I didn't even know about. Some of those talents turn out to be incredible in terms of physics. I had a student who struggled in the math, but every day she would come in, she'd ask me another question. She had observational skills I've never seen in any of my students in all my career. And she would ask me questions, and I'd say, when do you, she said, I'm always thinking of this stuff. I said, you know what, you should get a notebook and write these things down, because they're really good questions. I'll give you an example of a good question. She came and said, when you're sitting at a campfire, and somebody talks to you across the way, why do they have to speak so loud? And I said, I knew the answer. I knew the answer, but it was like I never noticed it. It was only because she told me about it. I said, this is a good thing to practice next time to see if it's true. What happens is the sound refracts because of the hot air until it goes over your head, so you have to talk louder because most of the sound is diffracting up. Now, I knew that, but I had never observed it. He was an example of something I knew from the books, but never observed. She observed it. She said, so about a month later, I said, did you ever get that notebook? She said, yeah. I said, are you writing things down? She said, yes. I said, oh, you didn't show it to me. She said, oh, I didn't know you wanted to see it. I said, yeah, I want to see it. She gave me this notebook, and it was like the Unabomber from Montana. Whatever. And there was like all the single space stuff, and it was just unbelievable. I had never seen anybody observing the world like this. It was like one question after another about observations when she walks down the street with incredible things. And here I was thinking, I said, now look, you're not good at math, but you are incredible at these observations. You have to realize that and find out what kind of job will make the best use of these skills. Don't let the math be your barrier. And then I was talking to a friend of mine who's a PhD MD. He said, she would be an incredible physician. Hadn't even thought of it. Observational skills, knowing what's going on. So interesting. So let's talk about another differentiated instruction to give you another idea of how we teach physics for all. So here's a lens, and we all like to do the lens lab. So we'll see, how can we do a lens lab that's good for every ninth grader, for some ninth graders, for then a very select few of ninth graders, and then even one that will challenge most people in this room. Okay, also from Quantoons. So that we teach everybody that. Very easy, that all the light leaves this, and we can take two of the rays, one goes across, one goes down, this one goes down, and then we have that. And everybody can make this ray diagram. Everybody. Now, some people, though, we can say, those are two triangles. Again, my PowerPoint, I don't know how to do this. These two triangles are similar. And so if they're similar, we have height of the object is to height of the image as object distance is to image distance. So we have a ratio. Some kids can see the triangles are similar, and then you can tell them what you do with similar triangles. And some people are like, whoa, I'm going to go back to the ray diagrams. Then you can look at these other triangles, and now you say, oh, look, the height, these are also similar, alternate interior angles and right angles. And so the height of the object is to the height of the image as the focal length from here to here is to this distance, which is di minus the focal length. So I have two Ho over high equations, and I can combine them, and there I have my equation. If I do, I die. 1 over f equals 1 over do plus 1 over di. So that's how you derive the lens equation. Very nice. And some kids like this. Or other kids, well, they can't quite do that, but you know what? Take your experimental results. Can you make a graph of the image distance versus the object distance? Sure, I can do that. They all can measure the object, measure the image, measure the object, fill in their chart, make a graph, and they all have this wonderful graph. Some of the students, you could then say, what is that graph? And someone will say, it's a hyperbola. Or if they haven't done that in math, you can say, this graph is called a hyperbola. And if you take numbers like xy equals a constant, 12, 3 times 2, 2 times 6, 6 times 1, 12 times 1, 1 times 12, that's the graph you get. xy equals a constant. So we can look at this and say, oh, this is not quite xy as a constant because it's displaced from the x and y axis. But of course it's displaced by 10, which turned out to be the focal length. So if we then look at our experimental data of di minus f and do minus f and multiply those two, let's see what number we come out. We always come out with 100. Some students, you could then say, I want you to play with that and see if you can get an equation. And so you get do minus f times di minus f equals f squared, and you do a little of this stuff, and then you get if I do, I die again. Some students. But then there's you people. So this is, again, I realized I have it here. I can do this because that was one of my other talks. This is the split image. I'll tell you the problem, then I'll make it exciting so you can have a minute to think about it. So here's a lens, and the question is, if you have a point source and a lens, what do you see on this side? I only do it with arrows. No, just a point on the axis. What does that look like? Can you make an arrow? Well, we'll talk about that later. But then we're going to take this lens, and we're going to break it in half. And then we're going to separate the two halves by delta, a small amount delta. Now what do you see? And this problem, anybody solves it by the time we're out of here? Go to work. So I gave this to Tomas to illustrate. It was called Split Image. And he did this wonderful illustration. Let me read to you what Tomas said about this, and then I can talk to you about the solution to the problem, or you can close your hearing and tempt yourself. But after reading the title of this article, I decided immediately to use it for my illustration. Split is where I was born, where I grew up, a beautiful city on the Mediterranean coast of Croatia. Looking back on my childhood, Split meant always the most perfect place. The temperate climate, the azure blue sea, the town rich in history, founded by the Romans. But in 1995, when I drew this illustration, bloody war was raging, which shattered my image of a perfect paradise. The illustration shows the sunny past, but under the fractured lens, we see the sinister side, the destruction and death. Today, 10 years later, the fragment of the broken lens have grown together in one piece, and the light that passes through is pure and perfect again. Oh, by the way, Tomas has never studied physics. But he understands physics. He looked the stuff up in a book. He knows, oh, the light from the candle focuses over here, then it unfocuses, then it hits the mirror, and the angle of incidence, the angle of reflection, and then it burns the earth. He knows, oh, in the lens, the image is upside down. Tomas is is physics really for all? He doesn't know any of the math. No math at all, I promise you. And yet he can appreciate a lot about physics. In fact, he can make physics so personal that we can enjoy it, even though he doesn't know physics. So let's get back to this tough problem. Is anybody where you know, and I don't want to tell you this. So this is like when the Olympics are during the day and they try, and you're going to watch it at night. So so you turn your back, and I have to show this. So first of all, here's what the problem is, and then that's what we know. So if you know that, then of course this is the easy part. Then that's on the axis, so you know that this relates to that. But when you split this, you have this goes to this and this. Well, that doesn't earn you $1. But recognizing that this is now this and this, all of a sudden reminds you, S1, S2, 2 point sources. What does that do for me? And that's where the problem gets hard. And by the way, you also have other light coming through and diffracting over here, which, so you can still earn it, go to work. Even though I gave you most of the answer, go to work. So lenses, which is real physics? Is it ray diagrams? Is that real physics? Because all 9th graders can do that. Is it solving qualitative problems with DO, DI, and F? If I move it closer to the lens, what happens? Oh, it gets bigger. Oh, it's upside down. Oh, it's right side up. 9th graders can do that. Can they derive the lens equation geometrically with similar triangles experimentally from graphical data? Oh, whoa. Some 9th graders, not all. Let's give them that opportunity also. Let's differentiate the instruction. Or if the lens breaks in two, lenses plus light interference, good luck. That's one of the problems. The problem came from the International Physics Olympiad, where we used to train, we still do, find the top 20 kids in America in high school, train them for 2 weeks. These kids are unbelievable. And then 5 would represent the United States against 40 other countries, solving problems like that in an hour each, hour and a half. 3 problems, 5 hours. Problem-based learning is another way. I can't get by anything without talking about active physics. What do we do? So we develop a sport that we played on the moon. Create a museum display on the atom or the nucleus. Design an improved safety device for a car. Build a motor generator toy. All of these things include physics and applications and transfer of knowledge and making it interesting. And they're learning a lot of physics, though they're not doing vector cross products. What we're trying to do now in active physics is have active physics and active physics plus. So those extra math things we can have in the book, but you can skip that. You know, I love television. You know, when somebody says, when you watch a TV program, it's not like, oh, don't watch this if you haven't ever seen it before. They say, come on, you can watch it. Don't worry, just come in the middle, you can watch it. It's okay. It's only, oh, we have prerequisites. Oh no, you don't know. Oh, you were absent for 2 weeks. Oh, just kiss the year goodbye. You know, nothing else is like that in life. School shouldn't be like that either. If they miss a month of school, well, let's give them an opportunity to start over. There are kids the first month of school who don't do well because they never do well the first month of school, or because they broke up with their girlfriend, or because they were in an accident, or because they had mono when they were out for 5 days, or because they were in a fight in the cafeteria and were suspended for 5 days. You know, there are actually, some of us have a difficult 1 month at a time. But it doesn't ruin our whole year. There has to be a way to cycle through the physics, so you start over every 5 weeks. And let's see if you can do it now. Let's see if you can come to school every day for a few weeks. Not, oh, you missed when we did vectors. I mean, you know, I love this one. Kids come to your class in November, and they give you this little pass, and you say, oh, welcome to my class. I'm so glad to see you. So tell me about the physics you had in your other school. I wasn't taking physics. Oh, we were on block scheduling. We weren't going to start until January. And you're thinking, it's November. How did guidance do this to me? This kid does not stand a chance. So what you do is you give them the book and you say, just read the 8 chapters over the weekend and then you'll be up to date. And you know the kid has no chance. Yet we have to find ways to chunk the curriculum so the kids can come in November and you say, look, hang with this group over here. They're working on this project. Just figure out how the course works the next week. Next Thursday we start a brand new topic and you'll know how to do it. And that's what we'll do. That's what life's about. School is so artificial. Oh, you missed the first month, my goodness.